Have you ever just, looked around you and wondered, what is all this stuff? Seriously, from the phone in your hand to the air you're breathing, it's all just matter. But how in the world do scientists even begin to make sense of it all? Well, that's what we're going to do right now. We're going to break it all down. So let's just start with a quick little thought experiment. Think about it. A glass of salt water, the air you're breathing right now, and a big bowl of salad. What could they possibly have in common? It kind of seems like a trick question, right? But the answer is they all represent a really fundamental way that we classify pretty much everything in the universe. And that classification, it starts right here, with two huge families of matter. Everything, and I mean absolutely everything, can be sorted into one of two buckets. It's either a pure substance or it's a mixture. This is the first and most important split we need to understand. Okay, first up, pure substances. Think of these as the specialists. They are made of only one type of particle, and that's it. It could be a single type of atom, which makes it an element, like a bar of pure gold. Or it could be a single type of molecule, which makes it a compound, like pure water, H2O. The key is its chemical formula is fixed. It never, ever changes. Then on the other side of the fence, we've got mixtures. Now these are kind of the social butterflies of the chemical world. A mixture is just two or more different substances that are just hanging out together in the same space. But, and this is so important, they are not chemically bonded. They're like roommates, not a married couple. They're just sharing a container. So here it is, the real acid test. With a pure substance, like water, the hydrogen and oxygen atoms are chemically locked together. You can't just physically pull them apart. But with a mixture, like our salt water over here, you can use physical means to separate them, right? You could just boil the water off, and you'd be left with a pile of salt. That ability to physically separate the parts, that's the ultimate test. Now, let's dive a little deeper into that mixture family, because it has its own little branches on the family tree. See, not all mixtures are created equal. You can basically think of them as either being super evenly mixed or, well, chunky. So the really evenly mixed ones, they're called homogeneous mixtures. That prefix homo just means same. And in these mixtures, the different parts are blended so perfectly that the whole thing looks like one single substance. You can't see the individual bits at all. Think about sugar completely dissolved in your coffee. And those chunky ones we talked about, those are heterogeneous mixtures. Hetero means different, and here the composition is definitely not uniform. You can usually see the different parts pretty easily. The classic example is trying to mix oil and water, or just grabbing a handful of soil from your garden. And this just lays it out perfectly. With homogeneous saltwater, every single drop is identical. But with something like a heterogeneous salad dressing, one drop might have a little more oil, another might have a bit more vinegar. So the big question you always ask yourself is simple. Can you see the different components? Yes or no? Okay, let's go back to those perfectly blended, homogeneous mixtures for a minute. They're so common and so important that they actually get a special name all their own: solutions. But what does it actually take to make one? It's actually a super simple recipe. You start with a solvent. That's just the substance you have the most of, like water in our saltwater example. Then you add a solute. That's the stuff you have less of, like the salt. And when that solute dissolves completely into the solvent, voila, you've got yourself a solution. Now, this is what I think is so cool, because it totally shatters a common misconception. We usually think of solutions as being liquid, don't we? But check this out. They don't have to be. Alloys, like the brass in a trumpet or the steel holding up a skyscraper, are actually solid solutions of different metals all mixed together. How cool is that? But science just loves a good plot twist. Just when you think you've got the rules all figured out, homogeneous means you can't see the parts, nature throws us a real curveball. It turns out some mixtures are absolute masters of disguise. I mean, let's just take a simple glass of milk. To your eyes, it looks perfectly uniform, right? Totally homogeneous. But is it really a solution? Are those particles dissolved on a truly molecular level? The answer is nope. Milk is what's known as a colloid. It is the great pretender we were talking about. See, technically, it's a heterogeneous mixture, but the little suspended particles of fat and protein are just so tiny that they don't settle to the bottom. They just float around, giving it that smooth, homogeneous look. And milk is not alone.
Things like blood and mayonnaise are also colloids. So how can scientists tell the difference between a true solution and one of these tricky colloids? Well, they use light. It's so clever. If you shine a beam of light through a colloid, the larger particles will actually scatter the light, making the beam visible inside the liquid. That's called the Tyndall effect. A true solution would never do that.
So, we've gone from this huge, big picture view of mixtures all the way down to these sneaky little colloids. So now, let's zoom in even further, like way, way further. What is the fundamental thing that all of these pure substances are actually made of?
It all comes down to this one single concept, pulled straight from the notes for this explainer: the atom. This is it, the smallest possible unit of matter that still has all the properties of an element. Everything we've been talking about, gold, water, salt, even the fats in milk, it's all built from these incredible little particles.
But what makes one atom different from another? I mean, what makes a gold atom gold and a carbon atom carbon? It comes down to one single beautiful number: the atomic number. This is just a count of the protons in the atom's core, in its nucleus. It's basically the element's unique fingerprint.
Take a look at this number, 19. What does it mean? It's not just some random number. In the entire universe, this number defines one thing and one thing only. That thing is potassium. Any atom anywhere in the cosmos with exactly 19 protons in its nucleus is a potassium atom, period. If it had one fewer, 18, it would be argon. If it had one more, 20, it would be calcium. That single number is the fundamental code for an element's entire identity. It's everything.
So let's do a quick recap of our journey. We started big. All matter is either a pure substance or a mixture. Then we learned that mixtures can be homogeneous, like a solution, or they can be heterogeneous. We even discovered those tricky colloids that only look homogeneous. And finally, we saw that it all boils down to the atom, whose entire identity is locked in by one single number. And that brings us to the end. But really, now the fun begins. Just take a look around the room you're in right now. What about that cup of coffee, the glass in the window, the wood of your desk? Now that you have the framework, can you classify the matter in your world?